Okay, so this video is for the course ENGR 213 ODE, Ordinary Differential Equations. And in part 1, we're going to cover 5 techniques that we can use to solve a first-order ordinary differential equations. At school, we covered actually more than 5 techniques for the first-order ODE, but here I'm going to just cover the 5 most important techniques for the first-order equations. We have separable equations, linear equations, exact, non-exact, made exact, and then we have Bernoulli equations. So basically there are 5 techniques, 5 methods that we can use to solve a first order ordinary differential equations. The first example we're going to look is a separable equation, and this one, it has the form dy dx is equal to a function times another function. dy dx, this is the same as y prime. So the idea of solving an equation using this method is to put all the y dy in one side and all the x dx on the other side, and then you integrate both sides of your equations, solve the integrals, and then isolate y, and in the end you write y, an expression of y, so basically y of x is equal to blah 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 blah, and then you can also solve the initial value problem if there is a given value. So that is used to solve the c coming out of the integral. Let's look at this example. We have y prime plus x squared is equal to 1. And also given y of 0 equals 1. So in the end, the answer should be looking at y of x is equal to blah, 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 plus a c that comes out of the integral, and then we're going to use this IVP. We call this IVP, initial value problem, to solve the constant. Okay, so we're gonna write, personally I prefer writing y prime as dy over dx. So we're gonna transform this equation as y dy dx plus x squared is equal to 1. So we're gonna put x on the right hand side and y on the left hand side. And then we have this dx, which we can put to the other side. So we have y dy is equal to 1 minus x squared dx. Now we're going to integrate both sides. So do this to both sides. We have y squared over 2. Do we do plus c here? Well, we can do plus c, but we're going to do plus c to the right hand side. We're going to put a c term to the x is equal to integral of 1 dx minus integral of x squared dx, right? I'm just going to erase this as x minus x cubed over 3. And don't forget plus c. Now we can get rid of this 2 by multiplying the whole equation by 2. So we have y squared is equal to 2x minus 2 over 3 x squared x cubed plus, I'm gonna call c1. You know what? This is c1. This is c2. We don't need to do 2c because c is constant. A constant times 2, it's still a constant. So we're gonna leave it as c, but we can make it better by labeling as c1 or c2. So here we say c2. Now we don't have to take the square root of y because we can just use y square and then we plug in y of 0 is equal to 1 to solve the IVP. This is much easier than having a square root over the whole thing on the x. So we're going to sub y of 0 is equal to 1. So this gives me 1 square is equal to 2 times 0, so that's 0, minus 2 over 3 times 0 to the 3, that's also 0, plus c2. So that means my c2 is just 1. So now we can write everything as y squared is equal to 2x minus 2 over 3x cubed plus 1. And don't forget that we need to take the square root right now. So y is equal to the whole thing, square root that. And there we go. Our second example, or our second method, is called linear equation. To use this technique, we gotta make sure that the equation is already in the form dy, already in the form of dy over dx, or y prime, plus a function that we're gonna call p of x times y is equal to f of x. This is the general form. General form means you're gonna make the equation or your question look same as this form before you can use linear equation. So if you have a number here, then you're gonna divide the whole thing by this number. So basically what I'm saying is the question must be transformed into this format before you can use the linear equation method. Now let's say it's already in this form. What do? We're gonna use something called integrating factor. In short, we're gonna say IF, which stands for integrating factor. That is obtained from doing this integral, e to the power of integral p of x dx. And p of x is this. So whatever we get here, let's say, let's just call it IF, okay? Whatever is, could be a number, could be x, could be something else, whatever we have. Once we got this, we can plug in to the template equation. We're gonna call that as a template equation, which looks like this: d of integrating factor times y is equal to the same integrating factor times f of x, this, dx. Next up, we see we have a d here, so naturally we want to do integral. And integral and derivative, they are like opposite way of each other, so they cancel out. So this whole thing on the left hand side is just integrating factor times y, and then you're going to solve the integral on the right hand side, and then you're going to isolate y and blah 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 blah. That's how you solve an equation using linear equation technique. The example we're going to have is this. Before you apply the method, let's have a quick look at what we have here. You see, this is the general form we have, meaning if we don't have this form, we're going to transform the question into this form before we can proceed. Is this what we have now? Nope, because we have x as the coefficient before my y prime, and here is actually 1. So we're going to make sure that the coefficient is 1 before y prime. So my first step is actually to divide x to get rid of it. So we have dy dx minus 1 over x times y is equal to, instead of x squared, we have just x sine of x. Now I'm good to go. And let's identify what is my p of x and what is my f of x. P of x is negative 1 over x. Don't forget the negative sign. It's not just 1 over x, it's negative 1 over x, because in the general form, we had a plus here. And my f of x is the other side of the equation. Now I can use the technique by getting my integrating factor. The integral of 1 over x is just ln of x. And here's the trick. We're gonna put this negative by using the ln identities. Put this negative as a power of negative 1 to x. So we have e to the ln x to the power of negative 1. And what's magical here is I didn't know this before I took this course. I learned the thing there in the classroom. So e and ln x, or e to the power of ln whatever, is just equal to whatever, because e and ln, they cancel out. So here I got just x to the minus 1 power, or simply 1 over x. This is my integrating factor that gets simplified into just 1 over x. And now we're going to plug in my integrating factor into this template equation. So I have d of my integrating factor. Let me add my d here and remove my integral, because that's actually next step. D was removed by integrating it, but now let's do it step by step. So we have d times 1 over x, which is my if, times y is equal to my integrating factor times f of x dx. My f of x is x sine x, and this two, they cancel out, so it's just sine x dx. And then we're going to integrate both sides so that this two disappear, and the integral of sine x is negative cos. Don't forget plus c. And there we go. So we have an expression, and we're almost done. Next step we're going to do is to bring this x to the other side. And there we go for this equation. The next technique we have is called exact equation. What's special for this technique is that you don't know whether this is exact or non-exact, which is my next technique. So first step is to check whether the equation is exact or not. What does exact mean? Exact means this. Exactness means this. Something is equal to something else. What is this something? Del m over del y is partial derivative of m, which is a function of x and y, is equal to partial derivative of n over x with respect to x. If they are the same, then it is exact. If they are not the same, then that's my example number 4, the next one. So to use this exact equation should be looking like this. Right hand side 0, left hand side looks very strange. What is this? M of x is y dx plus n of x and y dy. M and n, they are basically a function or an expression that involves both x or y. Example, m could be x squared plus 4y, and n could be another example, say x minus y, something like that. It's basically a function of both x and y attached to dx and dy. Personally, I don't know why, but personally, I just prefer to put dx in front of dy. You may have this situation in a test, which dy is before dx. Why just make an unnecessary step? We put dx as the first term, dy the second term. Why is that? Because the rule says m is before dx and n is before dy, and then why does that matter is because when we take partial derivative is with respect to different things, one with respect to y, the other one with respect to x. So we're gonna make sure you're gonna know which one is m, which one is n. After identifying which one is m, which one is n, you're gonna take the proper partial derivative. Don't take m over x is del m over del y, not del m over del x. That would be wrong. So let's look at example here. Now we see we have a function or an expression that involves both x and y, dx, something similar, dy equals 0. This is a strong hint that we're going to use exact equation, but we're going to check if they are exact or not. So this is my m, this is my n. M is before dx, n is before dy. And now we're going to do partial derivative the opposite way. No, this is del m over del y. We swap. I don't know why, we just remember this. Is it equal to partial n over partial x? Right? So let's do m. How do you do partial derivative over or with respect to y is when you see y, you do normal derivative. When you don't see y, let's say this 5x, treat it as a constant. And the derivative of a constant is just 0. So basically, if you don't see y, ignore that term. Simple as that. When you see y, do normal derivative. So this is just 4, coming from the derivative of 4y. Same thing for x. If you see x, do normal derivative. If you don't see x at all, ignore the term. This 4 comes from the derivative of 4x. So they are equal. So we can say they are exact. We don't call it the same, we call it exact. Now, next step is we write this f of x, y. Basically what I'm saying is there is a function that involves both x and y that is equal to the integral of m dx. Or you can also do, let's say you can also do n dy. It's your choice. Me, I want less headache. I just do m dx. But this is also correct. So m, what is my m? Is my 5x plus 4y. For y, not for x. Now we're going to solve this integral. So integral of 5x is 5 over 2 x squared. What is the integral of 4y dx? Is just 4y times x. And instead of having a c here, because here we're dealing with a function, so what is the function that represents c? It's g of y. Here, I'm gonna make a small notes. If you do m dx, then here you do g of y as the constant coming out of the integral. If you do n dy, then you do g of x instead of g of y. But just do one of them. You don't have to do both. Just do integral m dx or integral n dy. Now, next step, we're gonna do a partial derivative. Let's say partial derivative of f xy with respect to what? Here we did dx, so we're gonna do the other thing, which is y. We're gonna partially differentiate this whole thing with respect to y. Easy. How? If you don't see y like this first time, 0, gone. Here you see y, do normal differentiation, which is just 4x. Using power rule, because it was 1, it's like 4yx, with y having the first power. So comes down, -1, gone. You're left with 4x. What's the derivative of g of y? G prime of y, like that. And then we're gonna say this must be equal to my n x of y. What is my n? It was 4x. Well, voila, we have 4x. The reason why I'm doing this step is to figure out what is g prime of y by making a comparison. So you can see 4x and 4x, they're the same, they're gone. So that means my g prime of y is equal to -8 y to the power of 3. And now we need to find y by integrating this, because you know differentiation, and then you integrate it, then it returns to what's before. So we're gonna do -8 times, so g of y is equal to -8 integral y of 3 dy. There we go. In the end, we don't write y is equal to blah 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 blah. We are allowed to write just f of xy is equal to, we have this expression, copy here, replace g of y by what we just found. There you go. Y to the power 4. There you go for this method. Identify what is m, what is n. Do del m over del y, del n over del x. If they are the same, then they are exact. Then you can proceed to this. F of x, y is equal to the integral of m dx, or you can also do n dy. But if you do m dx, in the end you have plus g of y. If you do n dy, in the end you get a plus g of x. If you do, let's double check. If you do integral of n dy here, I'm gonna change the color here. Say n dy, right? And we got 4x minus 8y cubed dy. So 4xy minus 8 divided by 4, 2y to the power 4 plus g of x. And then we're going to do fxy partial differentiation. Since we did dy here, then this must be dx, right? Opposite to this. So when you see x, differentiate. When you don't, that's 0 plus g prime of x is equal to m of xy, which is here 5x plus 4y. That means 4y can cancel out. My g prime of x is just 5x, and my g of x, if you integrate this, right, integrate this, got 5 over 2 x squared. Magical thing. They're the same, right? Like from here, you can write 4xy minus 2y to the power 4 plus 5 over 2x squared. This is the same as this, just in different orders. Okay, the next technique, or you can say part 2 of the following technique, the previous technique, is non-exact equation made exact. You can tell by the name that obviously something kind of went wrong if you are doing the equation using my last example. Something appears that they're not exact. What are you going to do? Okay, so we're going to use something similar in last example and something similar in previous examples, like the linear equation, I guess. And there's something called integrating factor here. So we're going to use that method again. Let's just jump to the equation right away. So if you look at this equation, well, your instinct is going to tell you that this might be solved by using exact equation, because it's something dx plus some other thing dy is equal to 0. So this is my m, and this is my n. Remember, originally m is before dx, n is before dy. Now, can we just solve using the exact equation technique? The answer is no, or we don't know yet, because you have to check if they are the same. If what are the same? This. Is it equal to del n del x, the partial derivative? If they are the same, then, well, that's going to be the same as what we did before. If they are not the same, then this is the case for this example. So partial y, we have just 4y plus 0, and del n del x, we got just 2y, and they are not equal. So we're going to make them exact by doing an extra step here. I'm going to just write this thing first, and I'm going to explain. What is my? My is the short term of this guy, and nx is the short term of this guy. So my my is just 4y, minus nx is just minus 2y, over n. Well, n is not this, but this, and let's say 4y minus 2y, let's just do 2y over the original one, n. We have 2xy. This simplifies as 1 over x. Here I said or, not and. So let's do or. Nx, which is this, minus my, that. So negative 2y over m. I have 2y squared plus 3x. Which is a piece of shit. Because there's no simple way to simplify this. So immediately, this is not going to work. And this is my IF. This step is how you choose your integrating factor to proceed. And you're going to choose your integrating factor such that it contains only x or y. Like here, in my integrating factor, it's just simple 1 over x. Unlike here, I can't even simplify this because I have both y and x, which is not good. So we're gonna choose the simple one. It's not gonna choose the simple one. There's no simple one here. It's only one IF. That's good. That's the one that you have either only x or just y. You can't have both x and y in your integrating factor because the integrating factor is e to the power of an integral d something, right? That d something, if you have both x and y in your integral, that's not going to work. Speaking of the integrating factor to the power e to the power of integrating d something, this d something follows what you have after you got your integrating factor. Here I had 1 over x, so it's going to be dx. If it was something that involves y and y only, then this is going to be dy. In this case, we have dx. So now we're going to do integrating factor e to the power of my 1 over x dx. This is equal to e to the ln x, and e and ln, they cancel out, so I have x. Next up, after we got the integrating factor, we gonna need to multiply my integrating factor back to my original equation, both sides, right? So here, if I put x into it, I got 2x y squared plus 3x squared dx plus, don't need the parentheses, 2x squared y dy is equal to 0. I'm gonna call this new m. It's still m, but a different type of m. New n. Now we're gonna check if they are equal. The exactness, the partial derivative, are they equal? This is equal to 4xy, and my del n, del x, is equal to, indeed, 4xy. And they are equal, so now they are exact. We can proceed using the exact equation technique. So there's a function of x and y such that the integral of m dx is equal to it. And which m is this? Is the new m, this one, not the old m. Old m is no longer useful. So 2 and y squared, we just put it outside of integral, we just integrate over x. And that is x squared over 2. 2 cancel out. So just x squared y squared plus, this is going to be just x cubed, because it's basically 3 over 3 x to power of 3 x cubed. And don't forget to add g of y. That's ugly y. And now, similarly, we're going to do partial derivative of this function that involves both x and y with respect to y, because we did dx here, so we're going to do del y. This x cubed is gone because it has no y, and g of y becomes g prime of y. It's also equal to my n of x, my n, right? 2x y. As you can see, this is my n here, 2x squared y, 2x squared y, very magical. That means my g prime of y is equal to 0. And if you differentiate 0 over y by g of y is any constant, because derivative of any constant is 0, right? You got 3, differentiate that, 0, a billion, differentiate that, 0. So do the other way around, to the opposite. You got 0, integral it, you got c. So in the end, you don't have to write y is equal to blah, 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 blah. You can simply write as f x y is equal to this, right? Because we just found that g of y is just 0. Sorry, g of y is just c. Voila. Let's go over again. First step, actually for these two examples, very, very important. Your first step is always to check if they are exact or not. If they appear the same, then exact. If they appear not the same, in this case, 4y and 2y, they're not the same, they're not exact. And then you're gonna choose your integrating factor, right? This is not integrating factor, this is like what you're gonna do to get integrating factor. I'm gonna erase this. 1 over x is not integrating factor. 1 over x is what you use to get the integrating factor, which is x. After you get integrating factor x, multiply x back to your original equation. So I just increase the power of x. And now you're gonna check if they are equal or not. Personally, I never had a situation where I checked the second time and they're still not equal. If that's the case, you're kind of cooked and I don't know what to do. I will be very scared if it happens to me in the final exam. But luckily, never happened. So most likely, like 99% of chance, the second time you do this del m del y, del and del x, they should be the same, unless you made a mistake before. So if they appear not the same again, then probably redo the question, like redo the this whole step before. And then after you got this, you do f of x y is equal to the integral of m dx, blah, 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 blah. Don't forget to add g of y and then do the partial derivative with respect to another unknown, the other one, which is x, which is y, because we just did dx here. So the other one is dy. And magically, this should be the same as your n. Like this, they're the same. If they're not the same, but congratulations, you made another mistake. And then you're gonna figure out what is your g prime of y. G prime y is 0 because it's not there in the on the other side. So g of y is just c constant, and then you put everything, and there you go. Okay, the last example that we're gonna do in part 1, first order ODE, is called Bernoulli equation. Its form looks very similar to the second example we did, the second method we did, the linear equation, because if you look at them, Bernoulli is dy over dx plus p of x y is equal to f of x 2 times y to the power of n, whereas linear equation didn't have this term, didn't have y to the power of n term. So if you simply see this, use linear equation. If you see an extra n y to the power of n, then this is Bernoulli. Bernoulli equation, personally, I'm going to say it's the hardest and longest and most complicated one in first order differential equations. It's kind of long. You're going to memorize the steps. You're going to memorize the templates. The templates kind of look nasty, honestly. You don't want to miss everything. You don't want to miss anything in the steps. And you're gonna be crystal clear of what you're gonna do this step and next step. So what's in blue is the idea. After you identify that this is a Bernoulli equation, you're gonna say u is equal to y to the power of 1 minus n being the original power of y. So Bernoulli equation is actually one of the method in what's called reduction styles. I don't even remember the names. Like it's like you use something to replace something, like the u sub being called to use u to replace something and then do that thing and then bring it back. Similar idea here. We have u is equal to y to the power of 1 minus n. After you got that, you plug in into this template equation, and then now you just turn it into a linear equation because there's no longer y to the power of something, but usually this makes your f of x negative, and then you just solve it using linear equation technique. Solve. In the end, you got u is equal to an integral of blah 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 f of x, and then you're gonna turn u back into y. So let's do an example. Let's do this. So we can tell that this is Bernoulli equation because we see we have y to the power of 2, y squared. This indicates that this is not linear because on the right hand side it is not simply a function of x. So we're gonna say let u is equal to, do we do this step right away? The answer is no, because we need to make it into the general form, which is like dy over dx has 1 in front of it, not x. So we're going to get rid of this x here. And that's why your equation may look a bit ugly. So we divide everything by x. We got there's no x. And now we're going to identify what is my p of x and what is my f of x, what is my n. This 2 comes from the power 2. P of x is equal to negative 1 plus x over x. My f of x, if you look at the original form, the standard form, it's the thing that's right before y to the power of n, and here there's nothing, so f of x is just 1. So we can say let u to be y to the power of 1 minus n, meaning y to the power of 1 minus 2, -1, or 1 over y, whatever you want. And now we're going to use my template equation. I don't know why my dx in the bottom always look ugly. I'd always need to rewrite it. Plus, we have 1 minus n, n is 2, so 1 minus 2 multiplied by p of x, and then u, p of x, is negative 1 plus x over x multiplied by u. This whole thing is equal to 1 minus n, so n is 2, so 1 minus 2 times f of x, 1. This is -1, negative, gone. This is just -1. So what we have here after simplified is du over dx plus 1 plus x over x times u is equal to -1. Now, my p of x is 1 plus x over x, and my f of x is -1. However, my next step is to do integrating factor, right? The e to the power of this, and to e to the power of integral p of x. My p of x currently looks like this, which is ugly. So we're going to simplify it by, so this is like 1 over x plus x over x. This is like 1 over x plus 1. This looks a bit easier to integrate. And then my f of x was -1. Next step, integrating factor e to the p of x dx. This is going to be integral of 1 over x dx plus another integral 1 dx. And this gives me e to the ln x plus x. And that means if you expand this, e to the ln x times e to the x, and e and ln x cancel out, so I have x e to the x to be my integrating factor. And now, actually from this step below is the same as using linear equation. Same idea, same steps until you reach u is equal to blah, 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 and then you turn u back to y. So now my integrating factor is x to the e to the x. If you remember from linear equation that I just did, my next step should be another template equation. d if, instead of y, I have u, because everything here is in terms of u, not y. Is equal to if times f of x dx. This is my second template, which is also the same as the template in linear equation. The only difference is we had y before, but here we had u, because everything here is based on u. So I have d, my if is x e to the x times u is equal to x e to the x times my f of x was what? -1. dx, integrate both sides, this is gone, so we have x e to the x times u is equal to negative integral of x e to the x is equal to negative x e to the x minus e to the x. This is a simple, well, let me just do it here. X e x dx, this is integrating by parts. So f of x is x, prime x is 1. G prime of x is e to the x, and g of x is e to the x. This times that minus this times that. So x ex minus the integral of e to the x dx, which is the same, x ex minus ex. And don't forget plus c. So let's just open it up. So x ex times u is equal to e to the x minus x e to the x plus c. This is ugly. You open this up, this becomes plus, right? And then plus can minus the -1. And now we gonna need to simplify u by dividing both sides x e to the x. So e to the x divided by x e to the x is 1 over x minus just 1 plus c over x e to the x. Final step, you don't leave u, you want y, and from my first step, u is equal to 1 over y. So here is going to be 1 over y is equal, I'm not going to copy this whole thing, right? And now, very last step, you do this whole thing. Inverse. There we go. So Bernoulli is pretty long, and you may have a bit of challenge to do when you're doing the integrating factor, because there's integral here. You just forgot that it's a easy integral, not some nasty thing. First steps, always to make sure you're in the general form. Here, what I mean is make sure it's 1 before dy dx. After you have the general form, you write down this. You're gonna memorize this template equation by heart. Otherwise, you can't even start this question, because look, this is pretty much your kind of first step, like first and a half steps. So if you don't know this template equation, you got absolutely cooked in the question, because your question is basically empty. Now, stop everything into the template equation, blah, 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 blah. Correctly identify what is f of x, what is p of x, what is n. Use the template equation. And then from here, everything is based on u. And then you solve this equation using linear equation technique that I covered before in example 2. Very long but not very hard steps. And then don't forget to turn u back into y, and don't forget to make it the real y, not just 1 over y, because u is always 1 over y something, right? Because u was equal to y to the power of 1 minus n, and usually here it's always positive, so it's 1 over y to the something power. And let's say if u was like u was equal to y to the power of 5, then what you can do is this whole equation to the power of negative 1 over 5, 1/5. The trick here is the power, these two powers, multiply them together must be equals 1. Negative cancel, 5 times 1 over 5 is 1. So you're gonna find the power such that when you multiply it to whatever you have here, gives you 1. And that's pretty much it for the first order differential equations. All the techniques, I just did one example. There's a ton of example from the book. So yeah.